Welcome to this explainer. Today, we're going to demystify the complex manufacturing processes that literally create the world around us. Have you ever wondered how raw, clunky chunks of metal become the meticulously crafted components inside your car, your appliances, or, even the devices you use every single day? Well, we're going to unpack exactly how that happens. Take a look around. From the tiny microscopic screws in your eyeglass frames to those massive multi-ton turbine shafts in hydroelectric plants. Anything with rotational symmetry has to be manufactured with unbelievable precision. We rely on these perfectly round parts constantly, right? Often without even a second thought. But actually forcing raw, unyielding metal to become flawlessly round, man, that is an intense battle of physics and engineering. Okay, so let's dive right in by defining the fundamental process that makes all of this possible, and that is turning. At its core, turning is a basic machining process where the part itself is rotated while a sharp cutting tool is pressed right up against it. So you're essentially spinning metal at remarkably high speeds against a stationary blade to systematically carve out a shape. It's literally peeling away layers of solid metal until that perfect, desired form emerges, like a giant high-speed apple peeler for steel. Here's our roadmap for today's explainer. First, we'll hit the art of turning. Second, the anatomy of the lathe. Third, a real-world look at a brake disc. Fourth, the rise of CNC. And finally, making holes, focusing on boring and drilling. Section 1, the art of turning. Let's start with this macro-level concept. Imagine a single point cutting tool, physically peeling away layers of metal in real time. As the workpiece rotates against that incredibly hard insert, the tool shears off material, generating what we actually call discontinuous chips. It's just metallic fragments violently flying off. And controlling how these chips form and break away is actually a massive part of manufacturing science. Why? Because long, stringy chips can literally tangle around the machine, generate immense heat, and completely ruin the final part. Nobody wants that. So the crucial takeaway is that this cutting action doesn't just happen by randomly mashing a blade into metal. It's strictly governed by 3 specific parameters. I like to call this the holy trinity of turning. First up, we have rotational speed. That's just how fast the part is spinning. Second is the feed of the tool, meaning how fast the blade moves laterally along the part. And third is the depth of the cut, which determines how deep the tool actually bites into the metal. Together, these 3 things dictate our overall material removal rate. And let me tell you, if you get just one of these wrong, you might break the tool, destroy your surface finish, or literally melt the workpiece. Moving on to Section 2, the anatomy of the lathe. Because to actually control that holy trinity of parameters with the extreme rigidity required, we really need the true workhorse of the factory floor. Enter the engine lathe. It is absolutely fascinating to think that the basic metalworking principles of this machine date all the way back to the late 1700s. But of course, today's engine lathe has evolved into a highly rigid, motorized powerhouse. It's fully capable of withstanding immense cutting forces without vibrating or bending even a fraction of a millimeter. Think of the lathe exactly like a high-performance vehicle. The bed is the heavy cast iron chassis that absorbs all the vibrations. Then you have the headstock. That's the engine driving the rotation and transferring power straight to the spindle. Over on the other side, the tailstock provides critical stability for long parts so they don't dangerously whip around. And finally, the carriage. That acts as the steering mechanism, smoothly guiding the cutting blade exactly where it needs to go. Section 3, Real World, the brake disc. Let's see how all this machinery builds into a tangible, real-world scenario. When an automotive manufacturer needs to produce a typical gray cast iron brake disc, tweaking those basic lathe parameters can literally make or break factory efficiency. We're talking about facing operations here. That's where the tool moves radially across the end of the spinning disc to create that perfectly flat, smooth surface. You know, the exact surface your brake pads grip onto every single time you hit a stoplight. The data on this is just incredible. By simply upgrading the cutting tool material from silicon nitride to cubic boron nitride, a manufacturer skyrocketed their tool life from just 40 discs to an astonishing 4,200 discs per edge. I mean, that perfectly proves that advanced material science is just as vital as the mechanical physics. And because the tool lasted so much longer, they weren't constantly stopping the lathe to swap out dull blades. This pushed their overall machine utility rate up from 82% to an incredibly efficient 94%, all while actually cutting faster. A total game changer. Section 4, the rise of CNC. And that brings us to the modern era of automation and advanced, complex cuts.
Now, while manual lathes operated by master machinists can certainly cut some beautifully intricate features, like carving screw threads into a round shaft using a coated carbide insert, doing that consistently, thousands of times a day at scale, well, that requires some serious computing power.
As the source material points out, computer numerical control, or CNC, totally transforms turning from a manual art form into an incredibly precise science. These intelligent machines use absolute position feedback and high-accuracy scales to automatically compensate for micro-errors in real time. They're making adjustments way faster than a human ever could, ensuring that every single part comes out perfectly, flawlessly identical. Section 5. Making holes, boring, and drilling. Now that we've mastered cutting the outside of a part, let's pivot and talk about shaping the inside. It is absolutely essential to understand this critical distinction in manufacturing. Drilling makes the initial hole by pushing a rotary tool straight into solid material. But boring? Boring comes in afterward. Boring utilizes a single-point cutting tool mounted on a stiff bar to enlarge that existing hole, perfectly straightening it out and refining its dimensional accuracy. Essentially, think of drilling as your rough draft and boring as the final polished edit. And when you're making those initial holes, you have some highly specialized options. The twist drill is your standard go-to choice, featuring spiral grooves called flutes to guide chips upward and out. For large diameter holes, you might use a spade drill just for its sheer stiffness. But honestly, the engineering of the gun drill is absolutely brilliant. Because chip disposal and intense heat are massive challenges inside a deep, closed hole, the gun drill uses built-in, high-pressure coolant passages running right through the center of the tool. This violently flushes out the metal chips so the tool doesn't jam up or melt. Okay, so whether you're turning the outside, boring the inside, or drilling straight through, adhering to a few golden design rules is crucial. Mainly, it prevents tool chatter, which is that terrifying vibration that completely destroys parts. First, you must minimize your cutting tool overhang. Second, you have to support the workpiece rigidly. Third, please don't design unnecessarily sharp corners that are practically impossible to cut. And finally, always rely on machines with high stiffness and damping capacity. If you follow these rules, your manufacturing process becomes beautifully economical and staggeringly accurate. From the brake discs stopping the very car you drive to the microscopic screws holding your glasses together, rotational machining literally makes every aspect of modern life possible. It is this wild symphony of extreme forces, advanced material science, and perfect geometry. So, knowing what it actually takes to scrape metal into absolute perfection, what invisible manufactured marvel are you going to notice next?